Snapshot isolation prevents read skew. But it doesn't prevent two transactions from overwriting each other's work. This is the lost update problem, and it's one of the most common sources of data corruption in real applications. The pattern is always the same: read a value, modify it, write it back. Two transactions do this concurrently. Both read the same value. Both compute a new value based on what they read. Both write their result. One write overwrites the other. Concrete example: a Wikipedia article gets two simultaneous edits. Both editors load the current text, version 100. Editor A makes a spelling fix and saves. The database records version 101. Editor B, working from version 100, adds a paragraph and saves. The database records version 102, overwriting editor A's spelling fix. The fix is lost. This same pattern appears everywhere: incrementing a counter, read 42, write 43, both write 43, one increment lost, updating a JSON document, appending to a list. Several solutions exist. Atomic operations let the database handle the increment without the application reading first. Update counter set value equals value plus 1 where ID equals X. The database makes this atomic, no interleaving is possible. PostgreSQL, MySQL, Redis, and MongoDB all support atomic increment operations. Explicit locking: select for update acquires an exclusive lock on the read rows, blocking other transactions from reading them until the lock is released. The application gets a guaranteed read modify write cycle. Compare and set: only perform the write if the value still matches what you read. If another transaction has changed it, your write fails and you retry. PostgreSQL and MySQL support this pattern. The lost update problem is the simplest concurrency bug. The next problem, write skew, is far more insidious. Two doctors, Alice and Bob, are both on call at a hospital. Hospital policy: at least one doctor must always be on call. Alice wants to go off call. She runs a query: how many doctors are currently on call? The answer is 2, Alice and Bob. Constraint satisfied. She proceeds to mark herself as off call. Simultaneously, Bob wants to go off call. He runs the same query. He also sees 2 doctors on call. Constraint satisfied. He marks himself off call. Both transactions commit. Now 0 doctors are on call. This is write skew. Notice what makes it different from a lost update: Alice and Bob wrote to different rows. There's no overwriting. Snapshot isolation and even select for update can't prevent this, because there's nothing to lock. The rows Alice and Bob updated are different. The problem is a race condition on a shared constraint. The invariant at least one doctor on call depends on the aggregate state of multiple rows. Each transaction read a premise: there are 2 doctors on call, and acted on it. By the time they both committed, the premise was false. Write skew generalizes across a huge range of real applications. Booking systems: 2 users both check if a resource is available, both find it free, both book it. Multiplayer games: 2 players both pick up the same item because both saw it available. Username registration: 2 users both check if a username is taken, both find it available, both register it. The pattern: a transaction reads something, checks a condition, and makes a write based on what it read. The condition was true when checked but becomes false by the time the write commits. The only guarantee that prevents write skew at the database level is serializable isolation. Weaker levels cannot prevent it. Write skew gets even stranger when the rows involved in the conflict don't exist at the time of the read. These are called phantoms, and they represent the hardest case for isolation systems to handle. Here's the meeting room example. Alice and Bob both want to book the same meeting room for noon on Tuesday. Both query the bookings table: is this room free at noon on Tuesday? Both see 0 bookings for that slot. Both decide to proceed. Both insert a booking row. Now the room is double booked. What makes this a phantom? At the time both transactions checked, there were no conflicting rows to lock. Select for update requires rows to lock, but there were no rows. The conflict materialized only when both transactions inserted. One fix is materializing conflicts: pre-insert rows for every possible resource slot. Instead of having an empty bookings table, create a row for every room time combination. Now Alice and Bob can select for update on the room noon row before inserting their booking. The lock exists before the phantom can occur. The book describes materializing conflicts as a last resort. It's ugly. You're creating rows to represent the absence of bookings. The schema becomes artificial. You have to pre-populate rows for future time slots. It's a workaround for a fundamental limitation of lock-based isolation. Phantoms and write skew are the book's argument for why you should care about serializability, not just snapshot isolation. Snapshot isolation is great. It prevents dirty reads, read skew, and lost updates. But it doesn't prevent write skew or phantoms. Developers who assume snapshot isolation protects them from all concurrency bugs are wrong, and the bugs that slip through are the subtle, hard to reproduce, hard to detect kind.